Well, with that, then we are going to go on now to panel two. Our second session is a panel discussion on the state of climate change in Southwest Florida. Our presenters are Dr. Joanne Muller from FGCU, followed by Dr. Wendy Graham from University of Florida, and concluding with Nicole Iadevaia from CHNEP with audience question and answer through Menti following the presentations. So with that, turn it over to Dr. Muller. Thank you.
Hi, everyone. I hope you can hear me okay. My name's Jo Muller. I am at Florida Gulf Coast University, and I'm an associate professor here and also the department chair of Marine and Earth Sciences within the Water School. So many thanks to Jennifer for inviting me along today, and also to SHNEP for organizing this really important conference. So glad that we're talking about this really important topic today. And I was asked to talk a little bit about the state of sea level rise and storminess in Florida, what we've seen, what we can expect in the coming years. And you'll hear from my colleague, Mike Savarese, later on this afternoon, and he's going to be talking about ways that we're actually going to try to mitigate some of these issues. So you can slide forward. Okay, so first off, I wanted to talk a little bit about sea level rise, and some of you on the call might already have a really good understanding of this, but I just wanted to make sure we're all on the same page. So, why do the oceans rise? And so this is a slide that I like to show my students. It's probably pretty intuitive to know that as glaciers are melting, in particular our two ice sheets, so Greenland and Antarctica, they're releasing fresh water into the oceans, and sea level is rising as a result of that. And you can kind of slide forward as I go through this slide. I think I have some numbers on there. Yeah, so this is actually the amount of water that's stored currently in the Greenland and Antarctic ice sheets. So if they completely melted, this is what how much water we'd be inputting into the oceans. But one of the major things that has affected sea level rise in recent history has been something that we call thermal expansion. So similar to when you put a pot of water on the stove to cook some spaghetti, sometimes it will overflow as the water actually expands as it heats up. So we've been seeing the majority of sea level rise, or at least half of it, is due to thermal expansion. And then we also have some regional effects here. So depending on where you are, you may also be seeing the effects of sea level rise to be more pronounced. And this could be due to things such as subsidence of the land. So for example, up around Louisiana, you have a lot of subsidence going on. And so the land is actually subsiding as sea level is rising around that. And also land that used to have ice sheets on the land surface are currently rebounding. So some areas actually the landscape is rebounding as sea level is rising. So they're actually seeing a decrease in sea level. What's interesting about all of this is here in Southwest Florida, because we don't have these tectonic effects, we kind of see this normal, what we call eustatic sea level rise curve, which I'm going to show you in a second. So you guys can slide forward. Okay, so this is the sea level rise curve. Actually, Noah was talking about this in the last talk, and this is actually the long record from tidal gauges. So you can see that gray record, or the yellow record with the gray error bars. That's a tide gauge record going back into the 1800s. And then you'll see that that little red squiggly line at the top is actually from satellite altimetry. So now we have these amazing satellites like Topax and Jason that are up there, and they're taking really accurate sea level readings within a millimeter. So nowadays we have much more accurate reads on sea level rise, but nonetheless, you can see that sea level rise, sea level has been rising since the 1800s, and we've seen about, you can slide forward or go forward, we've seen about 1/4 of a meter since 1870. Okay, so that might not seem like a lot, but on a landscape where we're very close to sea level, it actually is really impactful, and we're already seeing the effects of that, and I'm going to talk about that in the following slides. So you can go forward. And yeah, and like I mentioned, we actually, here in Southwest Florida, we generally follow this curve. So it's actually a really good location to study sea level rise. And like I mentioned before, Mike Savarese will talk to you a little bit about some of that this afternoon. So you can slide forward. Yeah, so these are some of the effects that we're seeing in Southwest Florida. Noah had talked a little bit about some of these effects, saltwater intrusion, and also the economic effects, which I'll talk about in a second. But here, when you sort of travel around, you can actually see the effects really substantially. This is actually the Rookery Bay National Estuary Reserve. Here you've got some mangroves that you can see actually on the foreshore. So typically the mangroves exist behind the foreshore. So you have the mangroves, the foreshore, and then the ocean. But you can see as sea level has risen, these mangroves have been encroached upon, and they're actually, these are dead mangrove roots that you can see in the foreshore. You can see on the right-hand side, this is a Saltern. So we have these, obviously these amazing barrier islands down here, but they're very low lying. And so what we think is that as you have these really high tide events, you have a little bit of washover of salt into the middle of these islands, and therefore the deterioration of the vegetation. And then you can see some scarping, some dune scarping. This is actually after Hurricane Debbie, which was a really low intensity storm. But we're seeing this effect of, sea level rise and then storms on top of that really affecting our coastline. So you can go forward. And then just a couple of other indications. So this is a freshwater marsh on the left-hand side, and this is the encroachment of mangroves actually invading that freshwater marsh. The right-hand side is a salt marsh, and here we have a phenomenon that Mike studies a lot. It's called pocking, and when the mangroves become really stressed, they'll die, and the peat degrades below it, and then you see these bays start to open up that we call pocking. And then we see this a lot on our coastline, and the East Coast sees it terribly a lot, is this sunny day flooding that you see on the left, the bottom left there. So you can slide forward. So in order to talk about like what's going on and what's going to happen in the future, we really obviously need to talk about greenhouse gas projections. And you're probably going to hear this term RCP come up today quite a bit. So these are representative concentration pathways. And so this is all kind of based on how much CO2 we think we're going to be emitting in the coming years. And you can see RCP 8.5 is the worst case scenario, and this would be business as usual. So taking into account the amount of emissions and then population increase until 2100. And then you see the other RCPs. RCP 4.5 would be the Paris Accord. And there's a lot of conversation, if you look to the right-hand side, these are the temperature projections based on those RCPs. And there's a lot of conversation about if we can just stay below 2 degrees Celsius. So you can see that RCP 4.5 on the right-hand side. And, Noah had talked a little bit about the effects, the economic effects in Florida. And I always talk to folks and obviously my students about this. If you can imagine the costs of 4 degrees Celsius in Florida, just in terms of air conditioning, and insurance, it's a really important conversation moving forward, and it should have us all really trying to focus on sort of trying to tackle climate change and coastal resilience in particular. Okay, you can slide forward. So these are the RCPs, a few RCP models from those from the CO2 concentrations. And you can see the IPCC's Intergovernmental Panel on Climate Change, their models from their 2013 publication. So here you can see the 8.5, the worst case scenario, and then RCP 2.6 in the bottom there in blue. So these projections are based, mostly on, that thermal expansion and melting ice that exists on land, so not sea ice. But then you can see actually the 2017 projections from NOAA, and you can see that there's quite a bit of difference. So some of these projections from NOAA, they have this RCP 8.5, a worst case scenario. They have sea level rise up, up by, greater than 2 meters by 2100, which is when you consider most of Florida's coastline is within 2.5 meters of sea level, that's terribly concerning. So you may wonder, why are these models so different? So, recently the models have become a lot more sophisticated, and they're taking into account things like feedbacks, in particular albedo. So that is the reflectivity of ice. So you can see actually on the left-hand side of the image how much sea ice we've lost in the Arctic between 1984 and 2012. So this ice does a great job of reflecting incoming radiation. So do the ice sheets, they're quite massive, and even any of the land glaciers as well. And so as we melt them away, they're exposing either the ocean surface or the land surface, and now those surfaces can absorb that radiation that's coming from the sun. And that further heats up the Earth. And then also, as this ice starts to melt, it melts more rapidly. And we're certainly seeing this with Greenland. Greenland is melting faster than we had originally predicted. So this is where these more current models or recent models from NOAA come in, where you see these really large changes in sea level. And I always think it's important to remember, even though, this ice is very far away from us, this melting ice is very far away from us, we are going to be some of the first to feel the effects. And then we also have some regional effects. You might have read recently that the ocean circulation is slowing down some, in particular Gulf Stream. And so what this means is that more water is kind of left to pool up along the coastline of Florida. So this is going to also raise sea level slightly for us, and also leave a bunch of warm water for us around Southwest Florida. And I'll talk a little bit about why that's really important, in particular to hurricane dynamics, in a second. So you can slide forward. Okay, so I'm gonna sort of transition into storminess, because you really can't talk about sea level and not talk about storminess, or they kind of go together. And this is just a satellite image of Hurricane Irma, which obviously for all of us in Southwest Florida was quite terrifying. If you want to slide forward. So why do we care about hurricanes and understanding hurricanes and what they're going to do in the future? They are extremely costly and devastating. So they cause the loss of life and create massive economic problems for us in the United States. At the moment, we predict hurricanes to cost us about $28 billion a year. This cost is expected to go up to about $39 billion per year by 2075. But it looks like these early estimates are actually kind of on the low side. If you consider, the 2017 season alone, just 3 storms were, responsible for anywhere between about $250 to $300 billion. If you just want to slide forward, I think I have some highlights in there. You can keep going. So these are those 3 storms that I was talking about: Harvey, Maria, and Irma, all very costly storms. Harvey and Maria, particularly due to their flooding, and I'll talk a little bit about that in a few slides as well. But we've had lots of costly years. 2018 saw the landfall of Hurricane Michael, which was a rapidly intensifying hurricane. And I'll talk about that in a second as well. And then the 2020 season was the most active on date. But as we all know, here in Florida, we got very lucky. We just kind of got missed by a lot of storms. That season saw 30 named storms in the Atlantic Basin. So if you want to slide forward. So this is just an image showing the return periods. So by return periods, this is the amount of time that exists between landfalling major hurricanes. So the red areas are the areas that see the most frequent landfalling hurricanes. And we certainly kind of fit into this particular area. So we get sometimes direct hits, we get backdoor hurricanes that are coming from the East Coast. So generally we're a pretty active area in terms of hurricane dynamics. And then you see that Cape Hatteras area and one of the other target points up around Louisiana. Where most of the state of Florida is within 2.5 meters of sea level. So, hurricane dynamics, obviously really important. So you can slide forward. This is actually an article that came out recently just showing the costliness of hurricanes and how important population increase is. It could actually be the most important part of the puzzle. So not only do we have warming sea surface temperatures, rising sea level, but we also have people just migrating to the coast like crazy, which is obviously great for our economy. But it also makes these events really expensive. And so you can see some examples of these events that made landfall in really high population areas. For example, Sandy, and then Katrina, Harvey, Irma, and the costliness as a result of just the population. So these dark blue areas obviously indicating really large population areas. And I'm going to talk about Hurricane Dorian in a moment, but I just want you to think about, if that particular storm, if that particular Category 5 hurricane had made landfall in the very highly populated east coast of Florida, how costly and devastating it would have been. So you can slide forward, and you can slide forward again, sorry. So what are we seeing with hurricane dynamics moving forward, and why? So in terms of what the scientists think, we kind of thought, okay, we're going to see an increase in frequency and intensity of hurricanes with a warming world, but we're actually not seeing any kind of discernible trends in the actual frequency, even though last year we saw obviously the most dynamic hurricane season, again, 30 named storms, which was a record. Since 1878, when we've been recording hurricanes, we haven't actually seen a discernible trend in the actual frequency of storms. But one thing that we are seeing quite clearly is a change, an increased intensity in the actual strength of storms. And this is the power dissipation index. This is work from Carey Emanuel. And it's essentially using wind speed to look at the actual power of the storm. So you can scroll forward. And this is the PDI through time. This is for the Atlantic Basin. And then if you can scroll forward again, this is an overlay of sea surface temperatures with power dissipation index. So one thing that we know for sure is that with sea surface temperatures increasing, the actual intensity of hurricanes is increasing through time. You see, and you can forward a little bit more, you can see there's a little bit of a discrepancy there during World War II when we weren't out there taking data on hurricanes. So you can scroll forward. Okay, so sea surface temperatures, they provide essentially really high sea surface temperatures provide rocket fuel for hurricanes. This is a sea surface temperature map just the day before landfall of Hurricane Dorian, which was obviously a devastating storm for the Bahamas. Sea surface temperatures were above 32 degrees Celsius. And, storms, in order for storms to generate in the Atlantic Basin and to strengthen, they only need about 28 degrees Celsius. And on average, the temperatures at this time of the year around the Bahamas were a couple of degrees higher than average for that time. And then we see this rapid intensification. And so we had a storm that rapidly intensified to a Category 5 within just 48 hours. If you want to scroll forward. So one of the other things that we're seeing with storms, and you may have heard about this, is the slowing down of the forward speed of the storm. So storms obviously have a rotational speed. That's where they get their category status, and that's what causes all the devastation to us. But also they have a forward speed. And what we're finding is the forward speed is actually slowing down. And this is due to the upper level winds. So because of climate change, we're seeing a slowing of the upper level winds that are the steering winds for the storm. And so the storms are slowing down, and this is problematic because a slower storm can push more storm surge, and it can also dump a lot more precipitation. And if you guys remember Hurricane Dorian, you can slide forward. Hurricane Dorian actually sat over the Bahamas for a good couple of days. At times it was moving at 1 mile per hour. So if you can imagine a Category 5 hurricane with sustained winds of 185 miles per hour moving at 1 mile per hour. And this is actually the storm surge map that you can see from the Bahamas, from Grand Bahama. That yellow outline was what the coastline was before inundation. So I think I'm out of time. I was going to show a couple more slides about some of the research that we're doing, but I think I'm going to kind of wrap up there. If you can just slide forward a couple slides, keep going. Sorry, you're going to have to go through this one a little bit more. So this is just the slosh model for Hurricane Donna. So this was probably arguably one of the last really, really intense storms that we had. We didn't have tide gauges back then. They actually put them in the year after Hurricane Donna. But this storms saw, anywhere between 13 to 15 feet of sea level rise. You can slide forward to the last slide. And I would just argue, so this is the population graph on the bottom right-hand side for Collier County. So when Hurricane Donna made landfall, our population was less than 50,000 people. Now we're a lot more than that, especially, obviously in season. But, the idea of, even 13 feet of storm surge in Collier and Lee County and our other counties is really concerning Charlotte County as well. So I'll kind of just wrap up there. And if you guys have any questions at the end of the session, I'd be happy to answer them.
Great. We're going to go right on to Dr. Wendy Graham. Thank you.
All right, thanks for having me. And you can go ahead and advance to the next slide. I'm Wendy Graham, Director of the Water Institute at the University of Florida. And I'm going to talk to you about implications of climate change on Florida's water resources. And one of the biggest challenges we have in projecting the implications of climate change is that although we can observe the climate is changing, it's really difficult to predict future climate patterns. And there's a variety of reasons for this uncertainty. First of all, at timescales shorter than a decade, ongoing natural variations are chaotic and difficult to predict. And for Florida, one of the weather patterns, the El Nino Southern Oscillation, is the one that causes a lot of variability in our climate and can be a challenge for climate modelers to predict. The second one is when you go to the next phase, we really don't know exactly how sensitive the climate system is to carbon dioxide emissions, and the ability to simulate the climate system response to carbon dioxide emissions, although we know the direction of change is limited, especially at the local and regional scales. And finally, something that Joanne talked about, we really don't know how we as humans will change our behavior, so we don't know what future emissions from human activities will be. So if you can advance, we have three kinds of uncertainty: the natural uncertainty, like the El Nino Southern Oscillation. Next, the scientific uncertainty of exactly how the climate system is working and how it's going to respond. And the third one is uncertainty about human behavior. So next slide. If we look at these various sources of uncertainty in the near term, within the next 10 years, natural and scientific uncertainty are the greatest source of uncertainty that we deal about. So the color intensity of this plot indicates the percent contribution to, in particular, prediction of temperature change uncertainty. And red means more uncertain and blue means less uncertain. So if you could zone in on Florida over the next 10 years, about 50% of our uncertainty is coming from natural variability that's hard to predict. 40% of uncertainty is coming from our lack of scientific precision, and much less, 10% of our uncertainty is coming about how humans are going to behave. So we deal with this by looking at a variety of climate models and starting with different initial conditions and seeing how they propagate through the system. Next slide. If you look out a little bit more to 40 years, the scientific uncertainty shifts to, the source of uncertainty shifts to that scientific knowledge. So really understanding the details of how the climate is working all across the globe. And in Florida, we have about 20% of our uncertainty coming from natural system uncertainty in about 40 years, 60% from scientific uncertainty, and then the human impact uncertainty starts to come up. We have about 20 years. So we deal with this scientific uncertainty by using a collection of different climate models that all are representing the system slightly differently to try to look at the range of possibilities. Next slide. And finally, once you get out 90 years, how we decide to deal with climate change is our biggest source of uncertainty. So if you look at here in Florida now, natural variation is small, less than 10%. Scientific uncertainty is about 20%. And 70% of our uncertainty about the climate that's going to be happening out in 90 years is that, how will we respond to it? So we deal with this by using the different CO2 emission scenarios that Joanne mentioned. So the RCP 2 to 8 possibilities, 8.5 possibilities. So next slide. So if we look globally at what the near-term changes in temperature are, and these are changes from a baseline that runs from about 1985 to 2005. So the first row are projections for the time period 2016 to 2035. So we're kind of right in the middle of that right now. The second row is 2046 to 2065, so a little farther out. The first column is winter temperature changes. The second column is summer temperature changes. And the third column on the right is annual average changes. And they're all for this midline scenario of RCP 4.5 that assumes that our CO2 emissions are going to increase to about 525 parts per million by 2050 and then stabilize around 575. Right now, I looked a couple of days ago, they're at 410 parts per million. So next slide. Next. So on these maps, the stippled areas are places where we have most confidence in the global circulation model temperature projection. So for our ensemble of 20 or more models, they're all predicting similar increases. So next. And you can see that we're generally confident about the temperature at the global scale, and we're confident that the highest increases are expected at the highest latitude. And you can see that far left, lower left, the highest temperatures are expected in the wintertime at the high latitude. So this is sort of a global projection of increases. You notice they're all positive, somewhere between 2 to 6 degrees Celsius. Next slide. When we look at the same plots for the near-term precipitation or rainfall projections, the first thing you might notice is not much stippling, not many dots on these maps. And so basically, we're not very confident about the global circulation model rainfall predictions, even at this global scale. So if we have 20 models, it means that some are projecting high and some are projecting low, and they're not zoning in on a single projection. And so on this map, blue is more rainfall, red is less rainfall. And if you could look into Florida, it looks sort of blue. So you might think, oh, look, 0, we're going to remain about the same. But that's not what this means. That means like half of the models say we're going to get increased rainfall, and half of the models say we're going to get decreased rainfall. So there's quite a bit of uncertainty there. Next slide. And one of the reasons for this uncertainty is that the global climate model resolution in Florida is pretty coarse. What these maps show, the square blocks, are the size of the model grids where these predictions are taking place. So on the far right, they don't even have the lower half of Florida in the model. So overall, the GCMs are predicting by 2050 a 1 to 3 degree increase in temperature from this 1985 to 2005 baseline. But the rainfall, it ranges from 20% less rainfall to 10% more rainfall. And there's a lot of reasons for these uncertainties. I mentioned the poor resolution. The other one is that the peninsula of Florida is pretty unique, and the climate affects Florida in a much different way than if you're worried about snowpack. in the Rockies or in the Sierra Nevada, we know temperatures going up, snow is going to melt. But the climate in Florida has a lot to do with sea breezes and ocean currents. And we need to downscale these models to get these details represented accurately. So next slide. So to get a handle on Florida-specific climate projections and their implications for Florida water resources, a group of us established the Florida Water and Climate Alliance. It was established with a few projects funded by NOAA beginning in about 2011. And the goal of the organization is basically to increase the regional relevance and the usability of climate and sea level rise data, specifically for the needs of Florida's water suppliers and water resource managers. So this is an open stakeholder scientist network. The partners that sort of established the network are listed on the bottom, but it is open. Our meetings used to be in person. They have been Zoom lately. We hope to get back in person next year or so. But if you're interested in the organization, our website's there. It's also on the list of organizations that were sent out for climate action. So the stuff that I'll talk about is stuff that the Florida Water and Climate Alliance has been doing. Next slide. So there's a variety of interest areas that different groups in the Florida Water and Climate Alliance are looking at. There's a group looking at how extreme events may change in the future. So Carolina Moran from South Florida Water Management District and Joanne Obisekera from FIU are working with USGS. Their work is funded also by the Florida Building Commission to develop some future storm depth duration frequency curves for the whole state of Florida. There's another group looking at trying to improve seasonal scale predictions. So a lot of the water managers, Tampa Bay Water, Peace River, Minnesota, their operations are driven by surface water supply. So if we had better seasonal scale predictions, they would know when to pump into the reservoir, when to use ASR, that kind of thing. So we have a project funded by NASA. We're working with a climate modeler, Vasu Mishra at FSU, and a group at UF is working with Peace River and Tampa Bay Water to see how those improve their operations. We have a group looking at long-term climate projections. That's what I'm going to talk about. And this group, I would say, has had less emphasis on sea level rise. We've been watching how the Southeast Climate Compact has been progressing, but we don't have any funded projects looking in particular at sea level rise. Next. So the project I want to talk to you about, because it's the closest sort of to this region that's of concern in this meeting today, is a project where we've been working with Tampa Bay Water looking at climate change assessment. So what we're trying to do is evaluate the ability of GCMs to reproduce retrospective temperatures. So these climate models have been run in the past. So how well do they do specifically at reproducing temperature and rainfall in the Tampa Bay region where we have observations to compare them to? And when we take the global climate models and we put them through Tampa Bay Water's integrated hydrologic model, how well do they reproduce historic hydrologic behavior? Once we feel confident there, then we look at the future climate projections and look at changes in hydrology. And we're looking at how those changes in hydrology affect their water supply planning and evaluate the risks to their future water supply. The next slide. And this is our framework. Basically, we start at the GCMs at the large scale, but I showed you those grid cells over Florida. That's much too coarse to think about small scale hydrologic response. So we use a variety of downscaling techniques to translate these global climate models to the finer spatial scales we need to run our hydrologic models. Then we take a look at how that climate information looks over Florida, use it to drive the hydrologic models for a variety of scenarios, and then look at the hydrologic impact. I'm going to show you some examples today focused on stream flow, but we've also looked at groundwater levels as well. Next slide. So this is a pretty complicated slide, and the first thing we look at is to compare these raw GCMs and the downscale bias corrected GCMs over the time period where we have data. So next. So this solid black line on the left is observed rainfall, long-term average monthly rainfall throughout the year, showing the summer rainy season in Florida. Next. What that line is, that gray line, is the average rainfall prediction across these 9 global climate models over the same period. So you can see it knows we have a summer rainy season, but it's not reproducing the local rainfall perfectly. Next one. And this is the variability across all the 9 GCMs. So we have quite a bit of uncertainty. Next. On the right-hand side, this is the mean evapotranspiration. So the water that is evaporated over the soil surface or transpired by plants. And again, the black line is the observed historic. Next. This solid grayish line is the average over the 9 GCMs. And next, this envelope is the variability across the 9 GCMs. So you can see that, next, all of these raw GCMs are biased, and they have to be bias corrected before we use them. And when you see it, particularly for the evapotranspiration, the observed data shows in May, we have the highest evapotranspirations. All the models think the highest evapotranspiration occurs in June and July. And we think this is because they're not getting our cloud cover right due to convective rainfall and that kind of thing. So we have to bias correct it back to reproduce our observations. So next. These little blue crosses are what all 9 GCMs collapse into after we downscale and bias correct them. So next slide. So next step is we put this retrospective rainfall into the hydrologic model and see how it reproduces history. So next. The black line is the long-term observed annual average stream flow. So this is the Hillsborough River in Southwest Florida, showing lowest stream flow in May, the 5th month, highest stream flow at end of the summer rainy season in September, the 9th month. Next. The blue line is the average stream flow across all our 9 GCMs. Next. That envelope is the variability across all 9. So notice that even though all 9 reproduced the annual average rainfall and evapotranspiration perfectly, the nonlinearities in the hydrologic system cause a little variability. But next, on the whole, the retrospective stream flow is okay. After this bias correction, the envelope of our GCMs includes our observations and the calibrated model, which is the green line that uses the actual historic observations. So next. So after that, we've gained our confidence in how the GCMs are doing in the region once we downscale it. Now we want to look to the future. What do these 9 models say about the future monthly change in rainfall and evapotranspiration and something we're calling water deficit, which is rainfall minus ET. So what water is left after the roots do their thing and the surface soil does its thing. And these are differences over 2 different future periods. The retrospective period is 82 to 2005, and then the blue lines are changes from 2030 to 2060, and the red lines are 2070 to 2100. I'm running out of time, but you can see next for precipitation, we see slightly higher mean precipitation, but quite a bit of variability around these predictions. Next. We see definitely higher mean evapotranspiration. It's higher for future 1 and even higher than future 2. And next, what this says is the water deficit, the rainfall minus ET, especially in the long-term future, 27 to 2100, is much lower in future months. So next, but we have a large spread. Go. So now we put this through our hydrologic model to see what's going to happen in the future. Next. So again, the dots in these box and whiskers plots are the mean stream flow across the 9 GCMs. Next. The red is variability in stream flow across the 9 GCMs. And next, we see that the blue is the retrospective period. The red is the near future, 2030 to 2060. The green is 2070 to 2100. We can see, especially as we move out into the future, we see lower mean stream flow in the summer months. And this is when Tampa Bay Water is typically filling their reservoir. And we still have quite a bit of range of uncertainty in these projections, but indications that there will be less water in the summer and implications for their water supply. Next. So what we wanted to do is combine these 9 projections of possible future hydrologic condition with a number, and we picked 8 projections of how water supply might be handled in the future. And the scenarios are just exploratory. They're not recommendations. They're not predictions. We just wanted to look at how the range of use of groundwater pumping could affect the water supply. And our goal was basically, do these alternative scenarios meet the 2045 urban water demand? And can they do it while maintaining the current environmental regulations on surface water withdrawal and groundwater levels? And basically they go from abandoning all groundwater pumping to increasing groundwater pumping. So next. Okay, so here is change in water available from the Hillsborough River to be used for public water supply in the Tampa Bay region. So they have a permit that says how much water can be withdrawn from that river given certain river stages and river flows. So next, again, we're looking at 2 different futures, future 1 and future 2. The range of this box plot is the variability due to the water supply scenario. And the 9 models are each of the box plots. So those acronyms across the bottom are the 9 climate models. Next. So in this particular case, you know, the top change indicates no groundwater pumping. And next, the bottom of the box and whisker plots we're increasing all of the groundwater pumping. And next. So what we can see is we have 2 climate models that predict we're going to have more water available from the Hillsborough River in the future. And next, 5 GCMs that are predicting decreased water variability. And that, you know, if you look at how we might manage water, there's not much we can do with changing pumping to affect this water availability. So next. All right, this is my last complicated plot here. But basically, we're doing a scenario discovery analysis to try to evaluate the ability of Tampa Bay Water to meet their projected 2045 demand and meet environmental regulations that restrict their withdrawal from the surface and to maintain groundwater levels beneath wetlands. Next. So across these graphs are the climate change scenarios, basically representing the change in precipitation projected. Next. The y-axis is the pumping scenario. Next. And we had 3 different cases where we had no reuse of treated wastewater, 20% of public demand supplied by treated wastewater, or 40% of public demand supplied by treated wastewater. Next. First thing to notice is without any change in climate and business as usual pumping is that black dot. And it's right smack in the middle of those red dots, meaning we can't meet 2045 demand and we cannot maintain compliance with existing environmental regulations. Next. And if we do not use wastewater effluent, treated wastewater effluent, either directly or indirectly to offset public water supply, there's only 4 scenarios that can meet the 2045 demand and maintain compliance with groundwater regulations. And they all assume the highest increases in rainfall. Next. If we move to 20% demand supplied by reuse, we have more scenarios that can meet demand and environmental regulations, but they all require that our climate gets wetter as well as hotter. Next. And then if we use even more treated effluent, we have more options, but you'll notice that they all assume, all the ones that are green, assume we have at least as much rainfall as we have now or more. And with at least as much rainfall as we have now, we're going to have to use much less pumping and much more surface water in order to maintain current environmental regulations. So next. Never mind, go ahead, since I'm running out of time. So some take-home messages. So we have global climate models. They predicted continental scales, and they're predicting temperature better than rainfall, and they're improving over time. We have to downscale these to finer scales to really look at the implications for water resource planning. Most of the models are consistent that by 2050, we can expect a 1 to 3 degrees C temperature increase, but the rainfall predictions are basically anywhere from 20% less to 10% more. When you put these together, there's a lot of uncertainty about our groundwater levels and our stream flows. Next. What we project about stream flow and groundwater varies based on our choice of GCM and water use scenario, but the largest uncertainty is attributed to GCMs. Of the 9 models we looked at, 5 to 6 of them projected decreases in water availability, and that even with active conservation and dramatic increases in the use of reclaimed water, current environmental regulations might have to adapt to future climate. So the current environmental regulations about groundwater levels beneath wetlands, we may not have those wetlands if we get to a hot, dry climate. And so something may have to give with the environmental regulations to adapt to the future climate. Thank you.
Okay, good morning. My name is Nicole Iadevaia. I serve as Research and Outreach Manager for the Coastal and Heartland National Estuary Partnership, or CHNEP. The CHNEP is responsible for working with local, state, and federal governments, as well as community leaders and nonprofits, to restore and protect water resources and habitat in our region. The partnership reaches from the headwaters of the Peace River in Polk County down through Charlotte Harbor estuaries and out to Glades and Hendry County in the Caloosahatchee River Basin. I will be giving a brief overview of the findings from our habitat restoration needs and habitat resiliency to climate change projects covering climate impacts on native habitats in Central and Southwest Florida on behalf of the members of our partnership, which includes scientists, resource managers, policymakers, and community members in this region who have been involved with both the creation and implementation of the plans. I wanted to acknowledge all of these individuals and their entities for contributions to this work. One of the things that we are going to talk about today actually is following the last 2 presentations is we're taking some of the information from the modeling that they talked about and applying that into modeling on what's going to happen with vegetative communities in our region with natural habitats. So the CHNEP engaged environmental science associates Wood and Kasha Environmental to create a habitat restoration needs plan for the CHNEP area to provide guidance for effective protection and management of natural habitats throughout Central and Southwest Florida region. Full implementation of the plan will have substantial positive impacts on the long-term sustainability of habitat, natural systems, and species populations moving forward. Given that there's always limited time and resources, we sought to document all the factors that could impact prioritization of identified preservation and restoration efforts. Using the best available data, we modeled potential habitat migration caused by climate change impacts, including sea level rise and changing groundwater availability, in order to provide recommendations for management and preservation to shifting and shrinking habitats. So shifts in habitat were modeled using the habitat evolution model. Results from the modeling effort include which habitats may be in actual decline or experiencing disproportionate losses, and which habitats may be increasing, and what stressors may be driving those changes. The model used predicts coastal habitat changes in response to sea level rise in Southwest Florida estuaries, as well as intertidal wetlands and coastal uplands. It uses a predictive GIS algorithm that incorporates actual microelevation data for coastal habitats. Habitat zones within the region can be defined for different areas based on the elevation of the area relative to tidal inundation and water levels. The results we will share with you estimate the change in size and distribution of salt marsh or Juncus marsh, which is low salt, freshwater marsh, mangroves, and salt-bearing habitats. You can see from this graphic that these habitat communities require different levels of salt and freshwater inundation to survive at their current locations. The tidal stratums refer to duration of tidal inundation. For instance, mean low water is the boundary between open water and mudflat or beach because it indicates the elevation at which the land is always inundated on an average day. So if the land is below mean low water, it's assumed to be open water. If the land is just above, it is either mudflat or beach. The Habitat Evolution Model, or HEM, is a refinement of the Sea Level Affecting Marshes Model, or SLAM, which is a public domain model. The inputs to the model include topography, vegetation, and habitat data as it stands currently, as well as past data, tides, NOAA projected future sea level rise rates, areas of freshwater influence, and soil deposition rates, also known as accretion. To estimate accretion, the model uses decadal sediment loads to account for the overall cumulative amount of sediment that enters marshes. The image here shows the modeled vegetation used. The harbor receives sediment from its watershed and tributary creeks. Sediment carried by creek flows during storm events is deposited into the harbor. Salt marsh or tidal accretion results from suspended sediment deposition due to storm events and tidal inundation, as well as from accumulation of plant biomass over time. This table shows the acreages for 2016 and the difference in 2120 for all the model runs. So when sea level rise rates are higher elevation habitats convert to lower habitat types. In the intermediate high scenario, there is less upland, freshwater marsh, high salt marsh, juncus marsh, and mangroves, and open water increases dramatically. You can see there in the box, the yellow box on the right. To follow along with some of the major findings and recommendations drawn from the modeling from these projects and the images presented here, it's helpful to focus on the mangroves shown here in red, and both the freshwater and juncus marsh, those are shown in light and teal green. We can see that the results illustrate an expansion of open water created by projected sea level rise numbers. Intertidal habitat is expected to decrease dramatically, over by 63% loss. Tidal wetlands will expand landward where suitable slopes and substrates exist. Coastal uplands will transition to emergent tidal wetlands. And then mangroves will encroach into and eventually replace existing salt marshes. So the salt marshes will be relegated to the tidal rivers and will need suitable salinity gradients and riparian slopes to survive. The expansion of mangrove habitats will be short-lived, as you can see in the last graphic, as they too are pushed out between open water and hardened shorelines. And I just have a couple arrows there so you all can see, which of these areas that we're talking about. Finally, I wanted to share with you the application of some of the recommendations that were made for the current management and planning based on previous findings. Because freshwater wetlands and eventually mangroves experience a pinch out between open water and hardened development, we will need to reserve upland habitats to accommodate landward migration. We also need to reserve areas in the floodplain that are publicly owned to prevent further hardening. So this is public parks and ball fields that could accommodate landward movement of tidal wetlands or increased flooding. We also need to work with agencies to ensure that minimum flows and levels are being attained in rivers so that suitable salinity gradients are available for salt marshes. Additional protection of native upland habitat is important in a number of ways. It provides aquifer recharge functions, supports migratory corridors for threatened species, such as the Florida panther, as well as space for rare habitats. The impact of climate change on inland communities are less well understood, but equally important to coastal areas. So the information presented here reflects the work that was completed for our region, where increased saltwater intrusion is not a factor, namely freshwater portions of the Caloosahatchee River estuary. This area does not receive tidal inundation due to the Franklin Lock, which is designed to prevent it. The partnership engaged, again, environmental science associates and Kasha Environmental to evaluate likely drying scenarios in the basin and subsequent habitat shifts in order to guide recommendations. As stated previously, in order to provide guidance for effective protection and management of natural habitats, analyzing which habitat should be targeted and understanding threats to that habitat created by climate change are absolutely critical. So average temperatures in Florida are increasing and are projected to continue to increase based on the current rise. The evaporation and plant consumption of water, collectively called evapotranspiration, as was spoken about in the last presentation, is directly related to temperature. So with projected increases in temperature, there will be projected increases in evapotranspiration. The type of vegetated land cover distributed in the landscape is driven primarily by access to water. Plant communities are adapted and compete based on this. Thus, a change in water availability or hydro period will lead to a change in land cover. There will be increased drying. Event-driven precipitation amounts will likely fluctuate by up to 10% above and below normal averages, as we learned in the last presentation as well. Evapotranspiration rates are projected to increase by up to 7%. So what we modeled was that basically the amount of water loss associated with increased rates of evapotranspiration still exceed those of increased precipitation, even taking into account variability. The decrease in effective precipitation overall will result in decreases in groundwater levels. So drier climate will lead to increased groundwater withdrawal for agriculture and potable supply as well. So we'll discuss habitat migration in response to these stressors. Plant communities will migrate with their statistical norms of depths of groundwater needed. So similar work found that plant communities are also moving poleward in response to rising temperatures, and there is an increased tropicalization in habitats. As increased events of cold snaps or warm events that keep certain habitats in check will be happening less and less frequently, which will impact those habitats moving into other habitat areas. So this modeled surface showing the percent time duration that groundwater is present at 18 inches of depth, so average depth. So the higher percentage, the wetter the area. So 18 inches of depth is important for the recruitment of new plants as seed germinate and shoot roots at the depth. We may use, so this is using South Florida Water Management District groundwater monitoring wells in the area, and then applying those with those decreased temperatures or increased temperatures and increased evapotranspiration rates, and looking at what would happen with groundwater levels in that area. And you can see that there's an increased drying just south of the river in that red spot. Green areas are areas where there is a little bit more water for the correct amount of time. So the hydro period essentially is not changing for those habitats. And those red areas is where groundwater, it's not happening at the same times for not the same length of times, and there's less available. So those hydro periods for those vegetative communities are shifting. The map here shows the spatial distribution of different levels of transition risk based on the previous graphic that I showed you for native habitats by the year 2060. So the current duration of soil saturation within 18 inches soil surface corresponds with the habitat maps. The native habitats with high transition risk centers around the monitoring well observations south of the river and the central southwest that have been observed to be drier. However, the habitats north of the river are in the low category because they are lower elevation and surrounded by wetlands with assumed hydrologic recharge connections. Using the information discussed on the previous slide, a likely drying scenario of 7.5% of less groundwater availability was chosen when we were looking at vegetative community shifts. This scenario factors into increased evapotranspiration rates, increases in well production in response to drying conditions, as well as increases in precipitation events. So the vegetation management recommendations evaluated current groundwater levels and likely changes on those based on rainfall, temperature, evapotranspiration, and increased use to understand which habitats are more in danger of transitioning, regardless of other management actions that are currently being taken. So the results demonstrated that some habitats will shift regardless of restoration efforts with this increased drying. So what we take from that is that it'll be more important to manage for the future and what habitats are more likely to move in based on altered groundwater availability and timing or hydro period, rather than using limited funding and resources to return to past conditions that can no longer be replicated. So here's a table that outlines some of the recommendations from the second phase of the report. These are summaries of habitat areas in acres and relative percent of probable transition risk with the 7.5% drying scenario that we talked about. The tables show that over 19,000 acres of non-forested wetlands and over 10,000 acres of upland hardwood forests are in high risk of transition. Recommendations from the report reflect the need to protect these higher risk habitats in other areas. but not to focus funding on restoration to a historical habitat that may not be possible due to less groundwater availability needed to sustain such efforts. And so why do we talk about this? As they talked about before, as previous speakers talked about, there is a little bit of uncertainty when we're talking about some of this modeling and moving forward, but we also need to continue to plan for a future scenario. So we need to take the best available science and apply it as soon as we can, and then continue to refine that science and refine our applications moving forward. So using the recommendations from the climate change studies, the next step in the project was to implement these into an overall habitat restoration needs plan. So the goal here is to make realistic and strategic recommendations for future habitat restoration and conservation planning, and to help stakeholders prioritize funding and restoration work in the coming years in Central and Southwest Florida. So we believe that full implementation of the plan will have substantial positive impacts on the long-term sustainability of habitat, natural systems, and species populations, which will be important moving forward and adapting to climate change. So to make this plan more impactful and useful, it was built to be utilized by not only natural resource managers, but also taking into account the needs for those planning for infrastructure projects and land use in order to be balanced and realistic, targeting strategically those habitats most in need of protection and restoration. Now we understand the need for the plan and the goals. I want to give you a brief view of how it was built. So the project used the best available GIS maps, documenting changes in historical current land use, historical soils and habitats, and documenting all planned restoration and acquisition projects, as well as listed species critical habitats and migratory corridors as they are currently, to create real targets and opportunities. And again, we seek to plan for the future by using the best available data and modeling to project habitat migration due to climate change impacts, including sea level rise and changing groundwater availability, in order to provide recommendations for management and preservation to shifting and shrinking habitats. So it's again, moving from research to application. So here you can see a summary of the results from the report and GIS maps created as we rolled them up into three major habitat categories: tidal wetlands, freshwater wetlands, and uplands. These results are acres of habitat presented as either targets for restoration or opportunities for preservation. We start on the left, preservation conservation opportunities, or PCO. These are acreages of private lands that are not under conservation easements or otherwise protected, but have identified as strategic habitat value by stakeholders and natural resource agencies that, if preserved, would expand existing preservation conservation lands into larger ecosystem units and consolidate wildlife migratory corridors. Reservation opportunities are areas that are under the public ownership but have not been hardened, like the parks and the ball fields that are recommended to be reserved from further development so they can serve as coastal buffers for the sea level rise predictions that we talked about. Management enhancement targets are public lands that are or under conservation easements and are native. So the recommended management actions are to enhance activities on these areas, such as prescribed burning or hydrologic restorations, to make them more effective habitat. And restoration targets are public lands that are under conservation easements or publicly owned that are non-native. And so these areas are mapped for restoration activities such as regrading and planting. So turning our focus again to the non-tidal freshwater Caloosahatchee River watershed to create results and recommendations for habitat restoration needs using the same methodologies outlined previously. You can see here on the left a table of acreages for each of the same categories we mentioned previously and how those are mapped on the right. And again, this takes into account vegetation shifts due to sea level rise. Or not due to sea level rise, vegetation shifts due to groundwater availability in this area. So I will leave you with a few final thoughts on the project. The importance of completing these projects was to better understand what the future of natural habitats will look like in a shifting landscape, so that resources and efforts could be focused on moving forward rather than returning to an unattainable past. Coordination of efforts to create region-wide landscape-level protection will be important to brace these habitats for future climate stressors and potentially protect unique areas that are shrinking and shifting. The map pictured here demonstrates how establishing both preservation opportunities and enhancement and restoration targets together, while accounting for likely future scenarios, helps guide management in a way that creates wildlife corridors and contiguous habitat areas. Often management activities can be very localized and specific. However, they can be more powerful when they are part of a larger plan and coordinated by multiple stakeholders working together towards one vision. And with that, I just wanted to mention you can find the full habitat restoration needs and habitat resiliency to climate change reports on the CHNEP website. We're also creating GIS interactive mappers that will be live on the CHNEP Water Atlas in the coming months. So there's actually a GIS interactive mapper for the habitat restoration needs plan, but there's an interactive mapper for the habitat resiliency to climate change models that I had shown you earlier. So again, what we're looking to do is, continue to refine the types of data that we're taking into account and trying to plan for the future for what this area is going to look like, so we can preserve some of those native habitats and protect them as best we can. So thank you again to CHNEP Management Conference members, ESA, Wood Environmental, and Kasha Environmental for their role in creation and implementation of this work. With that, I'll turn it over to you, Jennifer.
Great. Thank you so much to our panel 2 presenters. And now for those of you out there in the audience, please go to menti.com if you haven't already and enter this code displayed. If you've already logged in, you'll see a screen where you can start to type in questions for our panelists, and they're going to go ahead and see those in just a minute and take turns to respond to as many of those as time allows. All right, we have a couple test and trial questions there, but if you want to scroll down a little bit. All right, then go right ahead. Thank you, panel.
I can probably take a shot at the one in green. How do you address people who say the current evidence is not human caused but natural variation? So I'm a paleoclimatologist, so I study natural variation. And all of the other interglacial periods we've been in, we should be actually cooling at the moment, but we're warming. And you cannot create the warming that we've seen over the last 100 years or so with natural variation. It's impossible. The only climate model that will actually show the temperature change that we've seen over the last 100 years is a model that actually uses CO2 as the main driver. One of the other big evidences that I like to use when I talk to students about anthropogenic versus natural climate change is what we call fingerprinting. So if you think about the greenhouse effect, you have all these greenhouse gases and they're absorbing radiation and re-radiating back towards the earth. You would expect, as you increase greenhouse gases and therefore warming of the troposphere, you're actually going to see a cooling of the stratosphere because less heat is escaping. And we actually see that with satellites. So if this was natural variation, you wouldn't see those types of fingerprints. We also actually see carbon signatures in the oceans, in tree rings, in all these living organisms that are incorporating carbon. They're incorporating a fossil fuel signature. So they're all fingerprints, and there's absolutely no way that the temperature rise that we're seeing at the moment is natural variation. Again, we should be cooling. We should be going into an ice age very slowly, but we're not.
And I think I can take the question that's addressed to me. Maybe I should clarify what I said. And it is a little bit related to what Nicole said. Under certain of these climate projections, the ones that are hot and dry, even if we completely eliminate groundwater pumping, the climate itself can't maintain a groundwater level high enough to keep these wetlands viable. So this might be one of those places where you're shifting habitat to something else. So that was in response to our most extreme water use scenarios that were aggressive water conservation, 40% either direct or indirect reuse of treated wastewater effluent, and maintaining the current minimum flows and levels requirements in the Hillsborough River. That's when we completely shut down groundwater, we still couldn't maintain the levels required for wetland protection.
I'm just going to go ahead and address the ones about the CHNEP, the presentations being available. Yes, these. So we are recording today's summit altogether, and we will make it available through our YouTube channel, which probably can be found through our CHNEP websites in the coming days.
Well, I'm not a horticulturalist by any means, but I think eliminating plants that require external irrigation and fertilization is a good practice for homeowners.
I guess there's a question about sea level rise projections. What's the most likely? And I'd say it's probably somewhere between those two that I showed you with NOAA and the IC Intergovernmental Panel on Climate Change. I think for sure that these feedbacks that we're seeing because of melting ice are going to have a really significant effect. So I think the ones from the Intergovernmental Panel on Climate Change are actually on the much lower end. I think we can expect to see much more than 0.5 meter of sea level rise by 2100.
I see another question about the historic ET record. There's a variety of gridded data products. We in this project use the NL-2 data record. I think it goes back to 1979. We used that because it has hourly climate data for all the parameters required for the Penman-Monteith equation, which are a lot. There are PRISM data sets that go back much farther than that. Again, a gridded product. They're by NOAA and NASA and other federal agencies. The PRISM data sets go back further, but they don't have as much. They might just have precipitation and temperature, and it might be a finer grid, but daily instead of hourly. So we used NL-2, and I believe it starts in 1979. Our retrospective period for that project was 82 to 2005. That was the record that the hydrologic model was calibrated over.
I can take that one. What habitats are most at risk? So in our particular region, what our modeling found was that when we're looking at areas where sea level rise is impactful, salt marshes look like they are rapidly shrinking and disappearing and getting pushed out by mangroves. And even though you see a mangrove expansion in the modeling that we did, it eventually gets pushed out between open water and hardened development. And then there's also an argument to be made whether that's quality mangrove habitat that's being created. The other thing that we saw that was at risk was isolated freshwater wetlands, was very high risk in the studies that we did.
I guess the question about sedimentation, I'm guessing from ship wakes. It's not my area of expertise for sure. I know it's very regional to areas with a lot of shipping, but certainly in those areas, I would expect that their climate resiliency should be built around that as well.
There's a question about wastewater reclamation, and actually that's a pretty active topic in Southwest Florida right now. I'm about to be on a review panel, and the National Water Resource Institute has been asked to review the city of Tampa's proposal to inject advanced treated wastewater into the not the lower Floridan, but the lower part of the upper Floridan in an ASR type situation, and then withdraw it at higher levels to maintain their water supply. I don't know the details of the expense compared to desalinization. Desalinization certainly is a very energy intensive process. I guess the membranes are improving, but there's a lot of work going on in that area. That's not my personal area, but clearly, in my opinion anyway, we have to start thinking about the one water concept. Our drinking water is our wastewater, is our water recharging our aquifers, is our water supplying our springs and wetlands. So we can't, flush it once and send it out to the tide for sure.
I will handle the, does the habitat migration GIS analysis incorporate human features that might influence the ability for inland migration, e.g. Roads as barriers? So the modeling that we did take into account areas that were already hardened developments. And part of our recommendations are any of those were mostly removed from the modeling that we did. There's an assumption that those areas that are hardened developments will remain as hardened developments. So we did recommend, again, it was more the soft development of the ball fields and the parks. And, if an area was able to be recovered, then the recommendation would probably be a hydrologic restoration or a complete regrading of the area, depending on something like that. But we sort of assumed that hardened areas would remain hardened.
The question about the intense rainfall events, there is a project, Dr. Janthe Obisekera at FIU is the PI on that, working on development of statewide improved duration, intensity, frequency curve for rainfall events to be used for stormwater and that kind of thing. So it wasn't a part of this work. We were looking at longer term water supply issues, but other groups are working on refining the depth, duration, and intensity curves for use in design of stormwater systems.
I think there was a question about Antarctica too. I guess there was a couple of studies published just in the last week or so in Nature about new data coming out of Antarctica, particularly those ice shelves and the instability. We've been thinking that Antarctica would you get a greater accumulation in some areas due to snowfall because you have more water vapor in the atmosphere over Antarctica. So that's kind of offset some of the melting or the ice mass loss that we've been predicting in the future. But these new studies are showing real instability in some of these ice shelves and the potential acceleration and therefore increase in sea level as a result.
I see a couple of questions here on, what can be done locally moving forward with some of this information. And I agree, it's always important to move forward to what can we do right now, even though we'll continue to refine the science, how can we apply it right now? And I think, as far as our study goes, I encourage all of you, if you can, to support your local land trust, NGOs, things like that, in the work that they're doing, and to look at look at the policies that are up at your state, local, and federal government when it comes to land protection, because it's not just protecting these native habitats and these lands, but there's also, they serve another value, which is aquifer recharge, among a number of other things too. So I encourage you to support some of those things and to look into some of those policies that can protect some of these habitats, which will also in turn protect water quality.
All right, I think we have time for one more question.
There's a question about, will water desalination become more important? It's certainly a possibility, but if you think about the carbon footprint of desal, it's pretty high with the energy required. And the idea that we would remove salt from our water and use it to irrigate our lawns seems pretty crazy to me. I think it'll always have a place, especially, brackish water, and a place in, treating wastewater effluent. But the experience so far that Tampa Bay Water has had, it's a good drought proofer, but it's very expensive and hard to maintain, and one piece of a puzzle that has lots of pieces to find a solution.
Well, great. Thank you to our presenters. And we are now going to conclude panel 2, take a very brief break, and